Today I have something special lined up for you guys. I'm going to show you how to create a swirl function which will take an image and then you can give it an x and a y coordinate and a specific range and it'll generate a swirl on that image, which is actually non-trivial to do and you need a good understanding of some trigonometry to do it. So let's get started. Fire up JES or whatever editor you're using to manipulate images. This should also work. Now save this somewhere. I'm going to save it on the desktop. I'm going to call it s.py and let's get started. So let's define a function. I'm going to call it swirl, and it's going to take 4 parameters. The first one is going to be p, an image you want to manipulate. It's going to take cx, this is the x position in the image, and the y position, cy, where you want the swirl to occur, and this variable called underscore range, which will determine how intense and how large the swirl is. I didn't just put range because range is already a built-in function. Okay, so first thing, let's make a copy of that image, just because we don't want to be manipulating the original function that's coming in. Let's get the width of this picture with get width of pic and also the height. Next, we want to make sure cx and cy, for center x, center y, are less than the width and less than the height, otherwise they're not really valid values. So Python has a keyword called assert, which is really handy for this. So you just say is between 0 and width, otherwise just say cx is an invalid value, and copy the same thing and do it for cy. There you go, now we're validating our input and we can make sure they are correct. So next thing we're going to do is we're going to loop through our picture pic and grab the pixels we want. So for y in x range of the height and for x in x range of the width. But before we can grab the pixels we want, we need to calculate where we're going to pick up our new target pixels. And this is the complicated part with a swirl because they're always changing. And we need to find a way to grab that pixel in relation to what our range is, where our cx and cy are, and what intensity the swirl is at. Now, we need to keep all these things in mind when designing our algorithm. The next thing we actually want to calculate is theta. And theta will give us the degree to which to grab the next pixel with relationship to cx and cy, wherever those are. However, the problem is x and y are always changing, and we need a way to be able to determine what theta is with relationship to those. So I devised a new variable I'm going to call v for the variant, and the variant is just a value that depends on x and y. You can make up your own variant. It doesn't actually matter too much, but I found that these values work fairly well. So I'm just going to say float because we want this value to be a real number. So this is almost like the taxi cab distance, except we're squaring each term. And you'll see why I need this fairly soon. So if v is not equal to 0, I'm going to say theta equals the range divided by v. The range is also an arbitrary value that the user is going to put in. In fact, the range should probably be somewhere between, I don't know, 0 and like 10,000. I find works fairly well. So we have this value range between 0 and 10,000, and v, which is our variant. That's going to vary depending on where x and y are with relationship to cx and cy. And this value is going to give a pretty accurate value of theta, although you can play with the values and try to get it as accurate as you want. So the next thing we need to do is actually grab those new x and y values, given that we know what theta is. Okay, now let's try to make sense of these new x and y values. If you look at these two equations carefully, you'll see that the coefficients in front are simply constants, and that we're also adding x and y values at the end, so cx and cy, and this is just to reposition the swirl once we've done our trig business. But in essence, these two trig functions placed in each function are really the meat of what's going on. And I think it's best if we see what a visual representation would look like. So I'm just going to open Grapher quickly and show you guys. So the two functions I had right there were negative sine x plus cos of x, and the other one was just sine x plus cos of x. Now each of these functions represents the values of our new x and our new y. However, if you look at these functions and start to realize what they're doing, one of them is chasing the other one, if you like to think about it that way. So if this is the x function, it's chasing the y function. So as y fluctuates, x is following it behind. And our x-axis would be theta. So as theta changes, y changes value, and then x chases y. So you can think about it like that a rotation occurs as theta changes because y has a concrete value there, but a few degrees later, x catches up and is the same value y was. So that's why these functions work. They're just ways of getting one value to chase the other one after a certain amount of degrees. What we're going to do is we're going to use the MinMax functions. Oops, excuse me. So we're going to grab the minimum value, the maximum value between 0 and the minimum value between width minus 1 and new x, and we're going to grab new y to max 0 between min height minus 1 of new y. And this will just grab a valid value of new x and new y that is within the function. Awesome. Now we actually want to change the color of our pixel. So let's grab the current pixel. So get pixel. And we'll grab the pixel and the current picture P at X, Y. And our target pixel is going to be just get pixel at new X, new Y. There we go. And we're going to set the color of our target pixel to be the color of our current pixel. Just standard stuff. And now we can return pic. And if I didn't make any typos, this is all that there should be. Now let me pause the video and add a few comments. Alright, done. So one of the key things I forgot to mention was that if we make theta a constant value, it will not produce a swirl effect, but rather will just rotate the image in place by a certain number of degrees, or rather theta degrees. So this might be what you're looking for. However, if you have like a rectangular image, you'll still have part of the old image where the rotation didn't fill up the original image, so it looks a little weird. I'll give a demo later. Or maybe right now, since we're ready to go. So let's pick up an image. I have one ready. Alright. It is a rodent. I found this super cute rodent online. Check him out. Isn't he so cute? Oh my goodness. Alright, so what we want to do is, I just want to place a swirl right on his eye and just like blow it up and make him look crazy. So let's do that now with our swirl function and hope nothing blows up. So S is swirl. Actually, we need to find out where that point is. So just explore P, and let's find out where his eyeball is. So 423, 321. Okay. So S is swirl of P at 423, 321. And now let's give it a range value, let's say about 3,500. That might work. Uh-oh, we got an issue. Oh, we forgot to specify the picture it's in, so that's just pic, that's just the picture we duplicated. And now it's running. And it's done, so let's show what we've got. And here we have it, just the rodent with a pretty crazy swirl on his eyeball. Now you can see we've got a bit of issues with the swirling, as there's like some dashed lines in between them. I haven't figured out a way to get rid of them, but I'll leave that challenge up to you guys. One method is just to use some anti-aliasing to like smoothen out the image and try to get rid of these. Shouldn't be too difficult, as they probably come out pretty easily and you should be able to identify them. Now let's try this with a bigger range to see what happens. So let's put like 7,500. I'm betting a bigger range should cause a bigger swirl. Let's see. Yeah, I think it causes a slightly bigger swirl and also increased the pull. So it'll pull more pixels in within itself. You see like part of the rodent right here has a lot of white pixels that's like pulling in on itself. And his eyeball just looks like a black hole. I'm staring into it right now, and it just wants to suck me in. Well, let's try this with a constant theta. Let's see what happens. I think this takes radians, so I'm just going to say like pi divided by 4 or something like this. So, yep, his eyeball is fine. It doesn't matter which you put in for the range since we're ignoring it entirely. So this should rotate him 45 degrees. Yeah, you see, it does rotate the image, although it has those side effects. And I don't know why it left like a shadow behind. Interesting. Anyways, this isn't what I was expecting, but hey, it might be an effect a year after, so I just wanted to show that off. Anyways, guys, thanks for watching. Hope you learned something. This has been a crazy video, and I'll keep doing other crazy videos in the future. See you.